Originally, you could look at a URL and see the name of a computer, the name of a directory on the computer, and the name of a file in that directory. But that's no longer true. With the web being the way it is, anything can masquerade as anything else. The named file may not even exist. The URL could trigger a program to generate the file and send it to you. But that's okay as far as reading from a URL is concerned, because any valid URL acts just like a file, and you can read it that way. There are actually two ways to set up an input stream to read from a URL. This is an example of one of them. This example reads an HTML file, the home page of VTC. The first thing you do is create a URL object addressing the file you want to read. A call to the URL's openStream method opens an input stream you can use for reading. To read from the stream, you need to create an input stream reader based on it. Then a buffered stream is constructed so internally the internet can be read in more comfortable blocks instead of each character being read as you need it. Now the file can be anything. It can be an image or audio or whatever, but in this case it's an HTML file, so it's simple ASCII text. The readLine method is used in a loop to read the individual lines of text from the input buffer. Each line is displayed as it's read until they have all been displayed. Now several things can cause an I/O exception to be thrown. The text of the original URL could be badly formed, or you may not be able to connect to the website, or the file may not exist on the site, or the connection to be cut in the middle of transmission. And that's not all, but all possible errors will be reported by an I/O exception being thrown. Here's what happens when you run it. You can see the text of the HTML file of the VTC home page. You can read anything on the web that your web browser can read. All you have to do is create a URL object that addresses it. This is the same program, but with a variation on how the input stream is opened. This time, the input stream does not come directly from the URL object. Instead, the URL object is used to construct a URL connection object. Then an input stream is retrieved from the URL connection object. The program is all the same after that. This program is just like the previous one. The only difference is the extra step in getting the input stream. Here's how it runs. As you can see, the results are exactly the same as they were before. This is the text of the raw HTML. Using the URL connection to get the input stream has the advantage of being able to connect through a proxy. If you are behind a firewall, you may get an unknown host exception and not be able to connect. To be able to connect through the firewall, you will need to set these three properties. The first is proxy set, which is a flag set to true to indicate the communication is to be made through the proxy. The second one is proxy port, which is the port number on the proxy computer. And the third is proxy host, which is the name of the proxy computer. The name will, of course, need to be in the host file along with its IP address. The next lesson is about using your internet connection to write to a URL. Java can be used to write both client and server software. To talk over the internet, a program needs to be able to work with some of the most basic protocol items. The most fundamental of these is the IP address, which is a 32-bit number that uniquely identifies a computer. By the way, any computer on the internet is called a host. JavaNet INET address is the Java class that contains the IP address. Since every host has an IP address, and it also has a name. It's easy to translate a name into an IP address, and there are some special IP addresses. This program is designed to show you some ways of constructing an INET address object. The most common way to get an internet address is by the host name. You specify the host name, and a search through the files of a domain name server returns the address. It's a little more complicated than that, but I'm only concerned with the host end of things right now. This is my web server, so its address should be returned. The show address method displays the IP address information. For the local host to be able to communicate over the internet, it is required to have an IP address, and this method returns an object containing its name and address. You can also specify an address as an array of bytes and build an INET address object from that. The only other method in this example is the one that displays the names and addresses inside the INET address object. This method returns the 32-bit IP address as an array of 4 bytes. This is the normal way to work with an IP address because the order is important. The Intel hardware swaps bytes when it stores the 32-bit integer, so an array will stay in order. The 4 bytes contained unsigned 8-bit values, so they will have to be formatted this way so they won't show up as negative numbers. 2 of the Boolean methods are also called to test for this being a loopback address and whether the host is reachable. It is necessary to check for an I/O exception when checking whether a host is reachable because it communicates over the internet. Here's what happens when you run it. This first host is my domain name, and you can see that it is reachable. The INET address object contains both the address and the host name, and this is the most common form in which you will see the IP address displayed. This is the name and IP address of this computer. The IP address is sort of special. When you set up a local network, if you use 192.168, none of the local traffic will leak out over the internet at large. They act like a private address. This is another special address. This is the loopback address. Any messages sent to this address come right back to the host computer as if they had come from somewhere else. But that's not the complete address. You also need a port number. That is, while an IP address will locate the host, the port number specifies which program on that host will receive the message. The port number is a 16-bit integer. To send a message, you not only need to know the IP address of the host, you must also know of the port number on that host. There are some standard port numbers called well-known numbers, and a program will sit and listen for a message to come in addressed to a port number. For example, if you want to talk to a web server, you send your message to port 80. If you are sending email, you can package your message for the Simple Mail Transfer Protocol and send it to port 25. File Transfer Protocol has 2 ports. Port 21 is used for control and communications, and port 20 is used to transmit file contents. And there are thousands of others, most of which you'll never use. But if you decide to make up your own port numbers, you can do that too. But it's best to choose a number above 2,000. But even that's no guarantee that you won't collide with somebody. But even then, as long as you don't get your hosts confused, you should be okay. A server is a program that sits on a port waiting for a message to arrive. When one does, the server responds by replying or serving a message that contains the information requested. So, a server is silent and inactive and only responds to requests. A server only needs to know his own port number, not the address of any host except the return address, IP and port that's sent to him in a message. A client is the active partner in communications. The client must know the address and port number of a server to be able to send a message. It is always the client that initiates communications. Java has some socket classes for both client and server that can simplify the process of setting up internet communications. A program can be either a client or a server, and a host can have both kinds of programs running, so a host can simultaneously act as a client and a server. And that's what the next lesson is about, setting up sockets for communications. The Internet is made up of hundreds of protocols. One of them is TCP. The letters stand for Transmission Control Protocol. It's one of the core protocols of the Internet. It's so important that the entire suite of protocols is called TCP/IP. TCP can be used to establish a connection, and the sender can be assured that the message reaches its destination. It's used by email systems and for file transfers, things that need verification. And Java has it built into it in the form of sockets. A socket is an endpoint of a TCP connection. This lesson contains an example of using TCP to establish an Internet connection. Communication is always initiated by the client, so let's look at it. This is a very simple client. It establishes a connection, sends a message, gets one response, and quits. The first job is to create an INET address of the host containing the server. This demo is going to be only on this machine, so I put in the loopback address. A complete address consists of the IP address and the port number, and the two are combined in the construction of a socket object. This port number is just a number I made up. I tried to pick one that nobody else is using. We're going to communicate through this socket object. The socket is used to produce an output stream. And this stream works just like any other stream, so we can use it to create a print writer which handles text output. Of course, we'll need to receive messages from the server, so a call is made to get input stream, to get an input stream from that socket. On this end, it's just the same as any other stream, so you can add stream reading objects to it. In this case, an input stream reader and a buffered reader. And that's all there is to making a connection from the client to the server. The connection has been made. If for some reason it wasn't made by this point, the server wasn't ready or whatever, an exception would already have been thrown. The server we're talking to is designed to receive text messages, so here goes one. A simple print line method into the outgoing stream does it. Also, this server is designed to respond with a line of text, so a call to read line will wait for the next text to arrive and return it to you when it does. The text of the message is then displayed, and the program is done. Well, almost. To clean up behind itself, the streams and the sockets are closed. Now, several of the above methods can throw exceptions. The main one is the unknown host, but you can get an exception for a server not running or several other things that can happen with Internet I/O. Oh, by the way, you can use this program to make sure that nobody is already using the port number that you've selected. All you have to do is run it, like this. The connection was refused. That means that no program is listening to that particular port on the host that was addressed. In the next lesson, I will show you the server that this client was designed to talk to and show you how they run. In the previous lesson, a client program was designed to send a text string through a TCP link over the Internet to a server. This lesson describes this server and shows you how the two work together. The job of the server is to sit and listen to a port number and respond to any messages that come to that port. This is a very simple server. It listens to the port, detects a connection, reads the text from the connection as long as it remains open, and sends a response to every message it gets. At the beginning, a server socket object is constructed. It requires a port number, but no IP address is necessary because the only time it will need one is to respond, and the response IP address is in the incoming message. The call to the accept method causes the server socket to listen to the port for an incoming message. This message normally blocks until a connection is made, but it is possible to put a timer on it if you want. If you were to call set SO timeout before the call to accept, that would set a timer, and the accept method would throw a timeout exception if the timer expired while waiting for a connection. The return value from the accept method is a socket, and the socket is connected and ready for communications. From this point on, the program works the same as the client does. An input stream is to be used for reading messages, and an output stream is to be used for writing. The readLine method, reading from the incoming socket stream, will block as long as the connection stays open. When the client drops the connection, the readLine method returns null. On the stream, it's an end-of-file situation. Each incoming message is printed, and the socket output stream is used to send a response. This simple server closes after it has served this one connection. Here's how the two programs run. The first thing to do is crank up the server so it will sit and wait on the port. The server is now waiting on the port. By the way, a port number collision would be detected at this point. That is, if another server had been already waiting on the specified port, this program would have detected that and not run. You can't accidentally have two servers waiting on the same port. Now to run the client that we developed in the previous lesson. There, you can see the result on both ends of the connection. The message was received by the server and displayed. Then the server responded, and this is the message that came back. Then the client closed the socket and quit. That sent an end-of-file condition to the server, and it closed its streams and sockets and quit. Now this was a very simple server-client transaction. Normally the server stays alive and waits for another client. A server can actually talk to several clients at once, and that's done by starting a separate thread to handle each connection socket. In the next lesson, we'll start looking at a different type of sockets for clients and servers. An alternate protocol to TCP is UDP. The letters stand for User Datagram Protocol. A message sent by the UDP protocol is often referred to as simply a datagram. Datagrams are used for connectionless transmissions. For example, the World Wide Web uses UDP. Your web browser uses a datagram and addressing inside a URL to send information to a web server, and the web server responds with a web page in a datagram. Like with TCP, you can set up a client and server that work with sockets, but there are some differences. The main difference is it is a connectionless communication. This is a UDP client program. You can send any kind of information you'd like in a datagram because the data is just an array of bytes. In this example, we send and receive an array of character bytes just to make the message easy to display. In fact, when you start the client, you specify the message text you want sent on the command line. If you don't specify the text, the word count is sent. Now this client just sends one message to the server, gets one response back, and quits. It starts by constructing a datagram socket. This is a special socket and works in a different way than the one we used earlier in the lesson for TCP. You will notice that the UDP socket constructor does not require a port number. You can specify one if you want to. There is a constructor for that. But if you don't specify one, an available port number is selected for you. And you usually don't care what the port number is, so it's probably best to let it pick its own port number. The datagram itself is built from parts. One of the parts is the data of the message. In this example, we're using a byte array containing the characters of the string we want to send. The destination address is also needed. And for this example, the target is the local host, but it could be any computer on the internet that has a server running. We take these parts along with the port number and build a datagram packet. It is this packet that will determine the transmission. Everything is in the datagram packet. All that's left now is to send it. The sending UDP socket fills in the rest of the information, the return address and return port number, which are necessary to get a response. Remember, this is not a connected protocol, so it's going to be up to this application to recognize the response when it comes. The outgoing message is then displayed for this demo program. This client does expect a response, so a datagram packet must be built to receive it. This one is built with a 256-byte block to receive the incoming data. Then the receive method is called to get whatever datagram comes into the port. It will most likely be a datagram from the previously contacted server because who else knows this port number? When a message does arrive, the array of bytes in the message is converted to a string. That way it can be displayed. Then the socket closes and the program quits. In the next lesson, we will look at the UDP server that works with this client. The previous lesson described a client program that used a UDP socket to send a text message wrapped in a datagram. This lesson is about a UDP server that receives text in datagrams and responds to what it reads. This is the server. It sits and waits for messages to arrive on its port and acts according to the commands received. The first job is to create and open a datagram socket. On the receiving end, it is necessary to specify a port number because the client must know the port number to be able to address the server. The receiving of messages is done in a continuous loop because this server repeatedly receives and responds to messages until it receives a halt message. To receive a UDP message, you have to create a datagram to hold it. This datagram message body is a block of 256 bytes. This is a drawback of the protocol. You must make the datagram large enough to hold the largest message you could possibly receive. If the incoming message is larger than the datagram to hold it, the message is simply chopped off. So watch the size, it's important. You can query the datagram socket and find out the size of the incoming message buffer, but that's not a limit. You can also expand it if you need to. The default size is plenty big enough for this demo. The receive method is called to get a message. This method call blocks until a message arrives. You can set a timeout on it if you wish, but it normally makes sense for a server to wait forever for input. When the receive method returns a message, you can get its length if you need it, and you can get the incoming block of data as an array of bytes. A short historical note here. This interface was developed by C programmers who would simply create a union containing all the possible data formats. In Java, the format conversion is a little more complicated because you can't union the byte array with a struct. You will have to do your own data conversion. In this example, all the messages are text, so the array of bytes is converted to a string object, and the message is displayed. The count of the number of messages is incremented, and the message itself is tested for meaning. If the incoming message is a request for the date, a return message of the current date and time is constructed. If the incoming message is a request for a count of the number of messages, a return message is constructed holding that count. If the message is a halt command, the socket is closed and the server quits running. Otherwise, the incoming message is used to form a question. To construct the outgoing message, the string is converted to an array of bytes. To send a response to the client, it is necessary to get the address and the port number from the incoming datagram. A datagram is then constructed containing all the necessary parts, and the send message is called to transmit the message to the client. The server program then loops back around to get another message. Here's how the two programs run. First, the server must be started. The server is now waiting for a datagram. Let's start out by asking for the date. And the returned date is displayed, and we can do that as often as we like. We can now get a message count. So far, the server has received 4 messages. If you send a message it doesn't recognize, it responds with a question. However, if you send a halt message, the server stops running. In the next lesson, we take a look at some of the I/O operations available in Java.